This video is going to go through a quick introduction to vectors, how we add vectors, and what I feel is the best way to manipulate vectors. Some things to remember with vectors is that one, they have two components. They have both a magnitude or a length as well as a direction. So we end up representing vectors with an arrow. This length representing my magnitude and the direction obviously indicated by whichever way my arrow is pointing. When we add vectors, we have to add them head to tail. This is the head of my vector, that is my tail of the vector. And also, we can only add vectors of the same variable, meaning if we have two velocity vectors, we can add them together, but we can't add a velocity with an acceleration or a velocity with a displacement. We can only add vectors if they are dealing with the same measured variable. When we add one-dimensional vectors, it's really nothing different than simply adding the vectors head to tail. What that looks like is if we have two different displacements. So let's say someone started here as my initial position, and they walked to a final position, and then, now I just drew it separately over here, they had a displacement back. How would we add these vectors head to tail? So we would have our first vector here, A, and then our second vector, we're going to add it head, the head of my first one, to the tail of my second one. So there's the tail, plus B would look just like that. And then the answer, when we add vectors together, is called either the net vector or the resultant vector. And that is always drawn from where I started to where I finished. Right? So this is my net displacement, or the total displacement, or the resultant displacement, would be represented by this red arrow here. The more common situation we have with vectors is trying to add them when they're not in one dimension, when they're actually acting in two dimensions or in different directions. Example here is if we have, again, a displacement. We have someone who starts here, they walk north, and then they turn and they walk east, and they end here. We're going to see these vectors added head to tail. Head to tail here. And so my resultant, or my net displacement, would be from where I started to where I ended. That is my net displacement. So when we add vectors, our total is from where we start, the tail of where we start, to the head of where we end. And it doesn't matter if it's a velocity or an acceleration, this is what it's going to look like. A classic example, an example of when we might have to add vectors would be if we have a boat that is able to travel at 3 meters per second and it's going to travel straight across a river. Well, that river has water that's actually flowing as well, and that water is actually flowing at 4 meters per second. What we can do is we can understand that the boat is not going to go straight across. Instead, if there was no water, they would land here. But because there's water, they're now going to land somewhere down here. This is my initial position, this is my final position, and what I can figure out is how fast are they actually going to be traveling down the water. If we look at this, here's my velocity of the boat, my velocity of the river, and I can add those velocities together, even though they're in different directions, to determine really how far the boat, or how fast the boat is actually moving. To do that, we would have the velocity of the boat here, velocity of the boat, plus the velocity of the river. I'm going to draw it longer, velocity of the river, because this is 3 and this is 4, so it should be a longer arrow. And then this would be my net velocity, or my total velocity that they would be traveling. Whenever we add vectors, we really like them turning into right triangles, because in this case now I can just do Pythagorean's theorem to determine my net velocity. If this is 3 meters per second, and this is 4 meters per second, I can do a squared, b squared, c squared, or I can see that this is a 3, 4, 5 meters per second triangle. So my net velocity is actually 5 meters per second. let's say that the boat actually took 10 seconds to get across the river, right? Now our displacements should make sense in both our x direction and our y direction based on the velocity that we were able to calculate as well as the displacement that would take place. So thinking about this, the displacement across the river from here to here, if there was no water, 10 seconds, 3 meters per second would be 30 meters, right? That would be my displacement there. Their displacement downstream, not drawn appropriately, would be 40 meters. 4 meters per second times 10 seconds would be 40 meters. So how far did they actually end up from where they started? Their net displacement would be 30 plus 40 squared, and their net displacement would actually be 50 in terms of 5 times 10. And again, we see this 3, 4, 5 triangle when we add the vectors. So this displacement plus this displacement gives me my total displacement in this situation. Another example would be if we have an airplane that's traveling at 300 meters per second just by itself, and then there's also wind that is being pushed, we'll call it in a northeasterly direction at 45 meters per second. How fast is this plane actually going? As well as which direction is actually going to fly. So what we have to understand is the plane's not going to fly straight. It's actually going to be flying at some angle. And the plane's probably going to be going faster than 300 because some of this wind is actually pushing it and assisting it as it's moving. So what we can do is we can add the vectors of these velocities and look at what's the actual net velocity of the plane. To do that, I'm going to take my vector of my air and add it to the vector of my airplane. So 300 plus 45. Now, our net velocity would look like this. Or my total velocity would be head to tail, or from the tail of where I started to the head of where I ended, because I've added the vectors head to tail. This is a little bit more challenging to solve. We could do law of sines or cosines, but the way that is typically done in physics is breaking this vector up here into its x and y component and then adding those together. So what we can do, because this one is at an angle, and let's say, for simplicity's sake, it is at a 30-degree angle, okay? We can then say there are components. So this is the y component of the velocity of the wind. This is the x component of the velocity of the wind. Now if you look, if I add the x and y components, we get the total velocity of the wind when they're added head to tail. So what I can now do is determine the velocity in the x and the velocity in the y by using sine, cosine, and tangent. If I look at this, the cosine of 30 degrees is the adjacent x over the velocity of the wind. The sine of 30 degrees is y over the velocity of the wind. Right? So those are ways that I can solve for the x and the y component. The velocity of the wind, so here's how I would designate it. The velocity in the x direction of the wind is the velocity of the wind times the cosine of 30 degrees, and the velocity in the y direction of the wind is the velocity of the wind times the sine of 30 degrees. In calculating each of those, I got the velocity in the x direction to be 39 meters per second, and the velocity in the y direction to be 22.5 meters per second. What I can now do then is break that up and show, okay, how would I find my total velocity? It would be the velocity of the plane plus the velocity in the y direction of the wind plus the velocity in the x direction of the wind. And notice I've added all three of those head to tail. Now I can find my total velocity total, because this simply becomes 300 plus 22.5. So this side is 322.5, and now this side is 39. And I can simply do Pythagorean's theorem to determine my total velocity. So it's 322.5 squared plus 39 squared equals the velocity total squared. So I have to make sure that I square root in the end. I get a velocity of 325 meters per second. So that wind is actually causing this plane to travel faster at a total of 325. Even though the velocity of the wind is 45 and the velocity of the plane is 300, the plane is now traveling at this direction at 325. Now, what if I wanted to determine that direction? I wanted to find this angle theta, right? Or this angle theta. It doesn't matter. What we have to do now is use the idea of sine, cosine, and tangent. If I'm going to solve for this theta here, I can use either these two sides and use tangent, or I can use either of the sides in my hypotenuse and use cosine or sine. I'm going to use these two sides and understand that the tangent of theta is equal to opposite over adjacent. So 39 divided by 322.5. To solve for theta, then I need to do the arctan of 39 divided by 322.5, and that gives me an answer. Of about 7 degrees. So the plane, instead of going 300 meters per second north, is now going to go 325 meters per second at 7 degrees east of north as they're traveling. One of the key abilities we need to be able to do with vectors is to break them into their x and y components. And that's going to be super useful because typically vectors from now on are going to be acting at some angle if they're not purely in the x and y direction. So example, if we have a cannon that shoots something up at 90 meters per second, but this cannon is angled at 40 degrees. What we need to be able to do is break that velocity into its x velocity as well as its y velocity to be able to analyze its motion a little bit more simply than simply trying to use the 40 degrees throughout the entire thing. So what I can say is this 90 meters per second is going to have an x velocity and a y velocity. And I will typically designate components by using arrows that have an open head. Whereas vectors, so this is a component. Nice end there. Whereas a vector will typically have a closed head. Right, so a component has just an open, a vector would have a closed. And so what I need to be able to do is, if I know this angle here is 40 degrees, I need to be able to find both my velocity in the y direction and my velocity in the x direction. My x velocity is the adjacent side to my angle. My y velocity is my opposite side. So that's how we determine whether we're using sine or cosine, or if we know one of the other sides, we could also use tangent. In this case, the sine of 40 degrees, SOHCAHTOA, sine is opposite over hypotenuse, so that's the velocity in the y over the 90. To solve for the velocity in the y, then, I need to multiply each side by 90, and I can have my answer there. What I need to make sure is that my calculator is in degree mode when I'm solving using the degrees of 40. Cosine of 40 is adjacent, so that's the velocity in the x direction divided by my 90. So my velocity in the x is now 90 times the cosine of 40. And again, make sure in our calculator is in degree mode as we're working through that. So that's the simple way we're going to be able to break things into their x and y components, and that's going to be the easiest way as we move forward looking at two-dimensional motion, looking at forces, as to how we're going to deal with vectors and how we're going to add vectors, specifically when they're acting not solely in the x or y direction, but when they're acting at some angle. Breaking them into their x and y components is super helpful, because then we have things that are always going to be at 90 degrees, and we can add them simply, and then to find our total, in the end we could find, use Pythagorean's theorem, and we'll see that as we work through problems dealing with projectile motion, as well as dealing with forces and any other component of vector that we're going to use throughout the rest of the year.